All right, so now we're going to take a look at a topic which is a way of representing these differential equations you've been solving. And that's called the slope field. So you were used to looking at something like this where we'd solve the equation. And just quickly, we might as well take a look. You'd have dy equals 2x dx. And then when we integrate both sides, this would be y equals x squared plus a constant. Which, you know, pretty simple, but I want to illustrate this to you what a slope field does. So a slope field is the graphical way to represent this situation. Rather than solve it algebraically, because some differential equations we can't solve algebraically, we can represent with a picture what it looks like. So it's really simple how you create the slope field. You simply use the values at a point to calculate the slope there. So for example, if this is how you define the slope equals 2x, then I know at 0, the slope is 0, right? In fact, everywhere along the line here where x equals 0, there's going to be a 0 for a slope. So I could do this pretty quickly along here. Then if I move out to x equals 1, what'll the slope be there? 2. So then we're going to draw our picture like this. Be a little steeper. And all the way down there it would be a 1. Now this is only because the slope depends specifically just on x. Some of these slopes you'll see later, they get a little more involved with calculating. But let's just do a little bit further. At 2, the slope would be good. So it's 4. We'll put a steeper slope over here. And what about at -1? What would I have there? Good. So it would become -2. So we'll put it in over here like this, going down now. And notice I'm just doing a very small representation because my picture would be very cluttered if I put lots of stuff in there. So I'm going to go over to -2 and I'll finish it off there. This would be -4, so fairly steep like this. But what this picture represents, and it's probably not something you'd recognize at the moment because you haven't practiced it a lot, but does anybody see the parabola in here? There are many, many parabolas in here. So let me just show you how this compares then. The initial solution at 0, -4, or if we knew this at 0, -4, and I wanted to show you what it looked like, then what I have to do is move my pencil to 0 and then -4. I'll do this in a different color. So that's what I know about the initial condition. And what I can do is use the slope field to show you what that would look like. And the way it works is you follow the direction that the slope is going. So by the time I get to here, that's the slope. You see I'm trying to make the slope match what's in the slope field. And then by the time I get to here, it should match again. And you keep trying to match that. So my slope field would give me a picture that would look kind of like this, and that's the parabola we've been talking about. If we put that in, 0 and -4, that means y equals -4. This would be -4 is my constant. So the particular solution algebraically is x squared minus 4. And if you look at that picture, that's the graph y equals x squared minus 4. So all the slope field does is it gives you a picture of all the slopes so that if you know the initial condition, you could sketch through the particular graph, or you could use the slope field to visualize the changes there. So if you think about probably the most common slope field that you'd see, anybody in geography? Nobody's in geography? Oh, okay, I'll tell Mr. Maloney. Has anybody seen slope fields anywhere before? Textbook? Yeah. Well, when you read a map, has anyone read a contour map?
Oh, you mean like the thing becomes the circle becomes smaller and smaller?
Well, where they start to show the elevations and the changes. So you look at a map and it's flat. But if you wanted to sort of convey where the steepness and the hills were, they actually do draw these on maps for some, you know, I know they look at this in geography anyways, but that might be the only other place you've seen it before. So we don't need to go that far with the application of it, but we are going to take a look at this one. So could you draw the slope field here and then show me what would it be, what would it look like at 1, 1, and then we'll try to solve it and compare to see if they agree, okay? So graphically, then do it algebraically so you can connect your picture to what your algebra was doing. There's nothing wrong with making a little x and y table if that helps you get going, but I'll probably just do a couple here. So x equals 0, then I'd have -4. So this would be a fairly steep negative. Okay. Uh-oh. What went wrong at x equals 1? Sorry? Asymptote divided by 0? Yeah, so we'd have a problem there. It would be vertical. There's a problem. So basically at this point, we'll talk about how you deal with this problem in your slope field, but at this point we're just going to politely leave it alone, and we'll see what its effect is in a second here. At x equals 2, it would be +4. And let's go x equals 3, we'd have a 2. And at x equals 4, I'm going to pick x equals 5. That's a nice one. So that would be 1. So I've got, let's see here, so 2 will be a little bit less. And then at 5, it's a slope of 1, so I'd go a little flatter still. Now, if I could sort of guess what's happening in the middle, it's somewhere in between, right? It's 4/3, so it's somewhere in between, you know, the slope here that I've got and this slope here. So, you know, you can sort of fill in the blank as being something in between those two. But can you see what's happening to the graph? Yeah, that's right. This one here, there's a vertical line there, right? The slope is vertical where it's undefined. And if I wanted to sketch through the point 1, 1, what happens? Well, we can talk about the algebra, yeah, because you can kind of demystify some of this with algebra, but it won't always be the case that you can use algebra to work around it. But what happens? What happens when you touch the asymptote? Your calculator explodes, right? You get an error. So this is just on purpose to illustrate a point to you. The way you walk through a slope field is you follow the direction of the slope. If I drop you off in a black hole, there's nowhere that you can go. You don't know where to go because it's undefined. You don't know where the next direction is. Life would be okay if we started, say, over here, because now I have a slope. I can say, go this way, then go this way, right? I can keep following it along. And eventually what happens is if I keep following those slopes, that's where I hit that vertical asymptote. So it would be okay if we got to out of the way of that asymptote, but whenever you have an asymptote, you can't go through there. Anytime it's undefined. I can't remember if I've put one in this lesson, but what has happened in say, an AP exam before is it might be undefined, and you basically, your graphs, you just have to remember that. The asymptote's a wall. When you hit that, you're done. You don't know where to go after that because you can't see the other side of the wall. The asymptote stops you. So even if it wasn't a vertical asymptote like this, if for some reason it was undefined, maybe it would behave really nicely like this, and you're really tempted to go through the other side and just draw a hole there. That would be nice, but you don't know what happens on the other side because literally this is where you're stopped. It's not defined. You're not able to go past it. So your graph is done. So that's all I wanted to illustrate to you with that is when things are undefined, you're either hugging the asymptote like this guy or your sketch is over because you can't go any further when you don't know what the next step is. It's undefined. You're standing at a place that doesn't exist. Okay, so if we want to solve this particular solution here, we might as well just solve it. We'll go dy equals 4 over x minus 1 dx. And we'd have, let's see here, y equals 4 natural log x minus 1 plus a constant. And we can't solve it for the one that we had because when x equals 1, you'd have natural log 0, which is undefined. And that's what the slope field is trying to convey to us. It says I behave nicely except when you make x equal to 1. The other point that I gave you here, that one we can work on. So I'll put that one in as 2, 1. So y equals 1. You'd have 4 natural log 2 minus 1 plus c. This would be 1 equals 4 times the natural log of 1. And that's a 0. So I get that my constant is equal to 1. So this is y equals 4 natural log of x minus 1 plus 1. Okay. So for the one that I did show you, which is valid, that starting point is okay. That would be its particular solution. So again, that's the only thing I need to emphasize to you in a slope field. That's the only really tricky part of a slope field is don't get creative. When you hit a spot that doesn't exist, you're done. There's nothing else you can do about it. Okay. So this time it's going to take a look at the sine graph when you want to sketch this one. And my hint here is, yeah, you could get creative and put some nice numbers in, like, for example, pi over 2, pi over 4, work through that way. But why not just think ahead to the answer? Think about it that way. What would the answer be? If you know what the answer is, that'll help you sketch the slope field. So that's okay too, right? If you try to strategize thinking, okay, I know what this is, if I integrate it, you should know what those slope fields are going to look like. That's the easier way to answer this one. So are we having any luck thinking ahead? Just waiting for me to think for you. It would be negative cos, so that's exactly what I'd be thinking in my head about this one. And again, there's nothing wrong with putting the points in. It's just annoying. So, this is my illustration to you that if you strategize, it can make it a little easier for you. And this would be my negative cosine graph. Same thing on this side. Oh, sorry, hang on. So this would be my negative cosine graph that I'm using. And I'm then going to use that to think about what the slope is. So here the slope is 0. So let's take that one there. And we'll say, okay, all the way along here, the slope is going to be... stop it. There we go. All the way along here, the slopes are going to be a 0. Then, I look, it's going to kind of do this. If I wanted to trace one out, that might be a good way to see. Oops. So at, oops, sorry, I have the wrong scale here. That would, oh no, that's right. Never mind, false alarm. But that'll give me some indication like, okay, this is about the slope when I'm over here. And then it's a little steeper even still when I'm over here. And then this slope I could use like like that. And then it flattens back out again over here. And we could do the same thing on the other side. So that would give me the slopes that look about like this. Try and match up to my picture as best I can. And then again, it's a 0 when it gets over to this side. Yep. Oh, right. Yeah, I suppose it could. I'll probably get away with it in this one just because I'm sketching it. But yeah, I didn't look at my scale very good here. It'll probably, we'll see here. Maybe I'll get away with it. Take this out. That's not a bad slope field for that graph. But yeah, what Lisa's pointing out here is that I should have started here and then made my graph go to here. So we'll fake it just like that. There, perfect. Okay. So the one that I'm looking for is at pi over 2.5. So I'll get rid of this graph, the black one I have here. And the point that I'm going to originally construct is at pi over 2 1/2. So if I use that, it's going to go up to here. And then, let's see here. Something like this. So sort of like that. I'd probably get away with that. I'm sure that that would be fine if it was, it is a sketch. So, you know, basically as long as the generic shape looks correct, you're fine. How do I know it doesn't go down to -1? Because I'm cheating. I know that it's going to be, like you said, negative cosine plus a constant, and that will be amplitude 1. So yeah, I'm using my knowledge of the solution to help me get the graph as well. Okay. We won't solve it. But we are going to take, the last thing we'll look at is implicit. So when it's not just in terms of x. So this one is in terms of x and y. This one's not a bad idea to pick some points. We definitely want to pick the point 0, 0 because it's on our initial condition. And we also want to approximate the sketch for f of 1. So we're going to have to pick some points along here too. So why don't we say, let's just pick some whole numbers like this. Now, if these are my points, there are some ways still to strategize about what it's going to look like, and we'll talk about that to help speed things up. But typically, the AP exam would have 6 points. They bold them out for you, and you put the slope through the 6 points they give you. So this would be more detail than is required. But if you think about what would be some nice ones to pick, you have no practice yet. So what would be a good strategy? You could get rid of one of the variables. How could you get rid of one? Make it 0. So if y equals 0, it's strictly the value of x that's going to pick it. So x equals 1, slope equals 1. X equals 2, slope equals 2. X equals -1, slope equals -1. And then this will be -2. All right? Then if I look at the next one, what else could I do to make get some nice points out of this? If I make x equals 0, it's just the value of y. So it's going to be y equals 1, y equals 2, y equals -1. That's a little steep. And then -2. Okay, otherwise, looking at the points I have, 1, 1, well, that's 2. then this would be the point 1, 2. So you add them together, it gives me a 3. So basically it's getting steeper as I go up. What about if this point here, this is the point -1, 1. What's going to happen here? Yeah, it's 0. And you should be able to predict, if I move along this line here, it's all going to be a 0. Because that's where you've got x and -y, right? That's the line y equals -x. So it's be a 0 when you add them together. Okay, so I'll just quickly put some points in. All I'm doing is adding the coordinates together, but I'm just trying to illustrate to you how you could use a bit of strategy to go a little faster with it. So here, this is going to be, let's see here, -1 and +2, so that'll be 1. Then this is a 0. This one here will be 2 and 1, so 3, and then 4. And this one is at 1 and -2, so it would be a -1. Okay, so I'll just go put them through now. So it'll be -3, -2, 1. Oops. This is at 2 and 2, so this will be a 4. Oh, sorry, 0. This is -1, -2, -3, and -4. So you might also notice that as I'm moving along those points, it's going like 1, 2, 3. It's changing. If you're going vertically or horizontally, it only changes by 1 because you're only changing the x or the y. But there, in relatively short order, we have the full slope field, which is typically much more than you need. And here, we're going to sketch this point through 0, 0. So if I was here, the next place I'm going is directly to the right, because, well, I guess depending on your perspective, we're going this way and we're going this way. And then you have to picture what's happening as I go out. And as I leave there, I'm getting pulled in sort of along this way. And I keep getting steeper as I go. So something like that would be where the graph is going. And then as I go through this side, I need to line up to these slopes. So that means I'm actually going to end up going, let's see, like this. A little too steep. But that's lining up to the slopes there, and this one is lining up to these slopes here. So it's going to look similar to that when you start graphing it out. Okay, so slope fields, your new favorite topic, maybe? One thing I'll let you know about, there's tons and tons of slope field calculators. So here's what x plus y looks like. If we do this one here, we went from -2 to 2 and -2 to 2. So there's the graph I was trying to illustrate for you. And not great, not bad. But you can see this, it's getting stuck in the asymptote there. And my picture sort of shows that, right? It starts to level off flat here, which is good because that's what happens over here in the computer model, right? They obviously can draw a lot more slopes. And then it's curving up this way, which this graph is also doing. So if you're not sure if your picture is accurate, you can fire it in this to get more points on the slope field. The other thing to know is some of the questions in the homework to this section, they either rely on you having a picture like this, one which you could just print this and then draw the slope through. But you definitely don't want, some of them are like it says right there, use a computer to get the slope field and then draw by hand. It's practice drawing the solution. So don't, it'll take too long to do this if you were to draw all those. So maybe a detention for the next person who's late.